Welcome back to Very Ordinary Differential Equations. In this lecture, we continue our study of linear first-order systems of equations considering the situation with deficient real eigenvalues. So we saw in the system y prime equals ay, where a is a matrix of constants, that if there are n distinct eigenvectors, v1 through vn, with corresponding eigenvalues lambda 1 through lambda n, which do not have to be distinct from one another, then you can make a fundamental set of solutions by taking the eigenvectors times e to the eigenvalue times t. However, it is possible for an eigenvalue lambda to have geometric multiplicity smaller than its algebraic multiplicity. There does exist some eigenvalue if and only if the matrix A is not diagonalizable. So eigenvalues are those scalars lambda so that there are non-zero vectors v, which satisfy av equals lambda v. For any such lambda, it doesn't take a whole lot of work to show that the set of all vectors which solve the above form a subspace of the domain of the linear transformation A. And this subspace is called the eigenspace of lambda. Equivalently, the eigenspace is the null space of the transformation A minus lambda I, or lambda I minus A, whichever. And we found eigenvalues as the roots of the characteristic polynomial, the determinant of A minus lambda I, or the determinant of lambda I minus A. So the situation we now face is as follows. What happens when the dimension of the eigenspace is smaller than the algebraic multiplicity of lambda as a root of the characteristic polynomial, when the geometric multiplicity is less than the algebraic multiplicity? Now we've done something sort of like this before. Let's suppose we have y prime equals ay, and the matrix A does have an eigenvalue whose geometric multiplicity is less than its algebraic multiplicity. This is called a deficient eigenvalue, and the difference between the two multiplicities is called the defect. So for the sake of argument, let's suppose that A is a matrix, it has an eigenvalue lambda with multiplicity m and defect k. So its algebraic multiplicity is m, but its geometric multiplicity is m minus k. Now we've dealt with repeated roots in characteristic equations before, when we had a linear differential equation of higher order with constant coefficients. When there was a repeated root in its characteristic polynomial, we had a way to generate a fundamental set of solutions. So if we try to extend the way we've done it in the past, we might think that if v is an eigenvector, that v e to the lambda t gives me one solution, and maybe v times t times e to the lambda t is another. This would be a nice generalization of how it's worked in the past. But it's a little bit more complicated than that, unfortunately. Let's suppose that y1 is v e to the lambda t, which does solve y prime equals ay. Then I claim that v times t e to the lambda t absolutely cannot be a solution. Indeed, if I take the derivative of y2, so we have the column vector v times t e to the lambda t. Well, v is a column of constants. Okay, so I can factor that constant column out from the derivative. Now I apply the product rule under that derivative and distribute the v, and we get v e to the lambda t plus lambda vt e to the lambda t. On the other hand, since lambda has to be an eigenvalue of the matrix, av equals lambda v. So ay2 must be av te to the lambda t, because y2 is vte to the lambda t. If av is lambda v, I can perform that substitution right there. But notice what we now have. We have lambda vt e to the lambda t. That appeared right here. So it is y2 prime minus ve to the lambda t. Now, since v isn't 0, this is not 0 here. And v isn't 0, by the way, because it was a non-zero eigenvector for the eigenvalue lambda. So ay2 is y2 prime minus something that isn't 0. So this is definitively not y2 prime. So if v e to the lambda t does solve y prime equals ay, then t times that definitely doesn't. So the way we're going to handle deficient eigenvalues cannot be an exact analog to how we dealt with repeated roots of characteristic polynomials in the past. So we have to work through some general theory, and this is going to be a little unpleasant. If lambda is an eigenvalue whose geometric multiplicity is less than the algebraic multiplicity, in other words, if lambda is a deficient eigenvalue, How can we find enough linearly independent solutions involving that same exponential e to the lambda t? This is our goal. We want to find enough linearly independent solutions involving e to the lambda t as this fixed scalar factor. Now recall, if v is an eigenvector with eigenvalue lambda, then I can write AV equals lambda v, but we could also write A minus lambda I times v is 0. We're going to define something called generalized eigenvectors of A with eigenvalue lambda to be solutions to A minus lambda I raised to a power times the column vector v is 0. So if k is 1, this exactly corresponds to traditional eigenvectors. But if instead of just doing A minus lambda I do A minus lambda I to a power, apply it to the column and get out 0, we're calling that a generalized eigenvector. If A minus lambda I to the k of a vector is 0, but the previous power is not, then we say it's a generalized eigenvector of rank k. So rank k simply means A minus lambda I to that power of v is 0, but a previous power isn't. So it's the first power of A minus lambda I, so that A minus lambda I to that power of v is 0. Now eigenvectors, as remarked, are simply generalized eigenvectors of rank 1. Now we've seen that an n by n matrix may not have n linearly independent eigenvectors. But every n by n matrix does have n linearly independent generalized eigenvectors. The proof of this statement is way beyond anything we want to get into. Take it as fact. An n by n matrix does have n linearly independent generalized eigenvectors. In other words, it has a basis of generalized eigenvectors. So if lambda is an eigenvalue of algebraic multiplicity k, there must exist k linearly independent generalized eigenvectors associated to that eigenvalue. Now the span of those vectors is called the generalized eigenspace of lambda, and it is the null space of A minus lambda I to the k, where k is the algebraic multiplicity of the eigenvalue lambda. So now let's suppose lambda is an eigenvalue and v is a generalized eigenvector of rank k. We're going to denote v sub k to simply be v, which we started with, and successively define, if I apply A minus lambda I to vk, I get vk minus 1. If I apply A minus lambda I to vk minus 1, I get vk minus 2. In general, if I apply A minus lambda I times to v sub k, we're denoting that as v sub k minus I. So note, if I were to apply the matrix A minus lambda I raised to the k minus 1th power to the vector vk, well, this would now be v subscript k minus 1, which simplifies to v sub 1. Now what happens if I apply the matrix A minus lambda I one more time? Well, on the left, I would get A minus lambda I to the kth power of vk. But vk was v, and v is a generalized eigenvector of rank k. So what happens if I apply A minus lambda I to the k power to a generalized eigenvector of rank k? I must get out 0. Now observe, all of these vk minus i's are generalized eigenvectors of rank k minus I, because this is not just a 0. It is the first 0 in this chain. Okay, because this was specifically a generalized eigenvector of rank k to begin with, there is no smaller power of A minus lambda I that I can throw against v sub k and get out 0. So none of these are 0 until the last one, which tells me that along the way, each vk minus I, if I apply the matrix A minus lambda I k minus I times, I'll get down to this 0 with no zeros in between. So all of the vk minus i's are themselves generalized eigenvectors of ranks k minus I. This sequence of vectors is called the Jordan chain of the vector v, ending with v1, which is now an eigenvector of rank 1, a traditional standard eigenvector. So let's suppose vk is a generalized eigenvector of rank k. It generates a Jordan chain going down to v1. And remember, the way you generate a Jordan chain is to keep applying the matrix A minus lambda I, where lambda is the eigenvalue associated to the generalized eigenvector v sub k. So vk minus 1 is a generalized eigenvector of rank k minus 1, and it has its own Jordan chain, starting with itself and counting down. So we're going to say that a Jordan chain is a maximal Jordan chain if there is no possible vector v sub k plus 1, which would generate this as the next steps of its Jordan chain. In other words, there is no solution to a minus lambda I vk plus 1 equals vk. This would correspond to having a Jordan chain that can't possibly be made any longer. So we call it a maximal Jordan chain. Equivalently, this is to say there is no solution at all to a minus lambda I times any arbitrary vector v equals vk. So now we can define something similar. Let's suppose v is an eigenvector, a standard normal eigenvector, with corresponding eigenvalue lambda. We're going to construct a maximal Jordan chain that terminates in this standard eigenvector. Remember, any Jordan chain ends in an eigenvector. So if we start with an eigenvector, the goal is to construct a maximal Jordan chain ending in that eigenvector. So set v1 equals the eigenvector you started with. Then inductively lengthen the chain in the following way. Suppose we've generated a bunch of terms of the chain, ending in now v sub I. Find all solutions to a minus lambda iv equals vi. If no solutions exist, well, by definition, you now have a maximal Jordan chain ending in the v that you started with, v sub 1. Otherwise, pick a solution, call it v sub I plus 1, and try again. We call this a backwards generated Jordan chain ending with v. It's a Jordan chain, but we started at the end and worked to get higher and higher into it, so we call it backwards generated. So some general theory about these Jordan chains. All elements of a Jordan chain are linearly independent of one another. The length of a maximal Jordan chain associated to an eigenvalue cannot be larger than the dimension of its generalized eigenspace. And the dimension of its generalized eigenspace is equal to the algebraic multiplicity of that eigenvalue. There is no guarantee, by the way, that there is a maximal Jordan chain of exactly that length. It just can't be longer than it. The length of a Jordan chain is therefore bounded by the algebraic multiplicity of lambda. What it is bounded by more specifically is the degree of lambda in what's called the minimal polynomial of A, not the characteristic polynomial. The minimal polynomial is something else. We're not going to get into it. The only thing that's important is that the algebraic degree of lambda in the minimal polynomial of the matrix A is less than or equal to its algebraic multiplicity in the characteristic polynomial of A. Okay, we've done a bunch of talking about Jordan chains, backwards generated Jordan chains, generalized eigenvectors. What does this have to do with differential equations? Supposing the system y prime equals ay, we have an eigenvalue lambda. It has, for the sake of argument, algebraic multiplicity 3, but it only has geometric multiplicity 1. So let's suppose v1 is an eigenvector for lambda. Then let's suppose that v2 is a generalized eigenvector, so that a minus lambda I of v2 is v1. So v2 is a generalized eigenvector of rank 2. We claim that v2 plus v1 times t times e to the lambda t solves the system. Our initial guess was maybe just v1t e to the lambda t would solve it. We're now claiming that what you need to do is v2 plus v1t, where v2 is specifically a generalized eigenvector of rank 2 that satisfies a minus lambda I v2 equals v1. So suppose y1 is v1 e to the lambda t solves our differential equation. Also, a minus lambda I v2 is equal to v1. We're now going to show that y2, defined as v2 plus v1t times e to the lambda t, also solves the differential equation. So we start off by computing y2 prime. All right, we have this expression times e to the lambda t. It's a product. We're going to apply the product rule. So first, we can distribute this lambda down to get lambda v2 e to the lambda t and lambda t v1 e to the lambda t. Those are those two terms right here. Alternately, we can take the derivative of what's inside constant plus constant times t. The derivative is just the constant v1. So we get v1 e to the lambda t. So this is just the product rule applied to this function right here. All right, we go ahead and factor out that shared term of e to the lambda t. That makes our lives a little easier. Now, v1 was assumed to be a minus lambda I of v2. So replace this v1 with a minus lambda I v2. Now we can do some simplification inside these parentheses. Here, if I distribute this out, we get a minus lambda v2, which cancels this lambda v2. So all we have now are a v2, and here we have lambda v1, but lambda v1, since v1 is a traditional eigenvector, lambda v1 is just a v1. Now I can factor the matrix A out on the left, and since v2 plus tv1 was just y2 times e to the lambda t, of course, we now have y2 prime is ay2. Now in general, let's suppose v1 is an eigenvector with eigenvalue lambda, and I generate a maximal backwards generated Jordan chain, vk, vk minus 1, etc. Remember, the way you get from one term to the next building up is to find a solution to a minus lambda I times a vector equals the one you have. At some point, there will be no solution to obtain, and that's when you found your maximal backwards generated Jordan chain. So suppose we've done that, then each of the following functions are linearly independent and solve the system y prime equals ay. Well, we've got our standard v1 e to the lambda t. Next, v2 plus tv1 e to the lambda t. We just worked with that on the previous slide. The next function would be v3 plus v2t plus a half v1t squared e to the lambda t. The general form is vk minus 1t, a half, 1 over 3 factorial, 1 over 4 factorial, and so forth. You're dividing by factorials and multiplying by corresponding powers of t as you count your way through your backwards generated Jordan chain, all times e to the lambda t. So this, in general, will now give you k linearly independent solutions to the differential equation. All of this sounds quite terrible, but in practice it's not that bad. Given the system y prime equals ay, where you have an n by n matrix of constants, how are we actually in practice going to find our n linearly independent solutions? Find all eigenvalues in their algebraic multiplicity. Then for each eigenvalue, denote the algebraic multiplicity by m and find an eigenvector for that eigenvalue. Once you have an eigenvector, construct a maximal backwards generated Jordan chain, and let's say it's of length k. This gives you k linearly independent solutions according to the formula on the previous slide. And now I have k solutions for an eigenvalue of multiplicity m. If I have m total solutions, I'm done. Put that eigenvalue aside, move on to the next one. If you don't, go back to this step and find another eigenvector corresponding to this eigenvalue, which is linearly independent from the first one you found. Then repeat the process of generating Jordan chains and so forth. So pick an eigenvector, make a Jordan chain. Do you have enough solutions? If yes, move on. If not, find another linearly independent eigenvector and make its Jordan chain, and so forth and so forth. If you execute this procedure correctly, you will get exactly n linearly independent solutions. In other words, a fundamental set of solutions to the original equation. So let's try to put this into practice. Example, find a general solution to y prime is this matrix times y. So we find eigenvalues as roots of the characteristic polynomial. So we go ahead and set up a minus lambda I, take its determinant. This factors as lambda minus 3 squared. So there is only a single eigenvalue. It has algebraic multiplicity 2. Now we're going to look for eigenvectors. In the back of our minds, we're hoping for 2 linearly independent eigenvectors, but given what section this appears in, we kind of expect we're not going to find them. But let's try. So we go ahead and set up the matrix times our unknown column is 3 times the column. The first equation gives us negative a plus 2b equals 3a. The second gives us negative 8a plus 7b equals 3b. Both of them reduce to the same information. B is equal to 2a. So we can't possibly find two linearly independent eigenvectors. As soon as the value of A is fixed, the value of B is automatically fixed, and I can't let them both be 0. So the only possible eigenvectors are scalar multiples of A equals 1, B equals 2. So there was only one eigenvalue, 3. We were only able to find a single linearly independent eigenvector, 1, 2. So we say, that's too bad, now we've got to construct a Jordan chain, a backwards generated Jordan chain ending in the eigenvector 1, 2 that we found. Now note, we're actually only looking for one generalized eigenvector, because then we would have two generalized eigenvectors, and since we have a 2 by 2 system, that would mean we're done. So we solve. A minus lambda I v2 is equal to v1. So here is A minus lambda I. Lambda is 3, so I simply subtract 3 off the diagonal of my original matrix. So here's A minus lambda I. I apply that to my unknown vector v2, and what I'm supposed to be getting out is the eigenvector that we already found. So both lines give us the same equation, that negative 4a plus 2b equals 1. And all we need to do is find a single solution to this. One possible solution is given by a equals 0 and b equals a half. So we go ahead and set v2 to be that vector, 0, 1/2. So we now have two linearly independent solutions to our differential equation. They are eigenvector e to the eigenvalue t, and then generalized eigenvector plus eigenvector t e to the eigenvalue t. This means our general solution is of the form c1y1 plus c2y2, where y1 and y2 are given above. Now, since this is the first time we're doing this, let's make sure that we can't accidentally find even more solutions. So let's suppose we've found this generalized eigenvector. Can we extend the backwards generated Jordan chain one step further? In other words, is there a v3 so that a minus lambda I v3 is equal to v2? Well, a minus lambda I, again, lambda is 3, so we take 3 off the diagonal, and here's our new matrix. Here's our unknown, and here was the v2 we were hoping to get out. Now the first line forces negative 4a plus 2b equals 0. But the second line forces negative 8a plus 4b equals 1/2. The second line, however, negative 8a plus 4b is just twice negative 4a plus 2b. But 1/2 is not 2 times 0, so the two requirements contradict one another. In other words, there is no vector v3 that can possibly solve this. So it's not possible to extend the backwards generated Jordan chain any further. So we found that our procedure really did terminate itself at a certain point. Once we had the correct quantity of linearly independent solutions, this procedure was not able to go any further. Everything worked out nicely. For our second example, find the general solution to y prime is this matrix times y, a 3 by 3 in this case. So we compute eigenvalues of the matrix as roots of the characteristic polynomial. The determinant of a minus lambda I should be set equal to 0. Okay, if I subtract lambda off the diagonal and compute the determinant, it's negative 3 minus lambda times the determinant of what's down here, 1 minus lambda, 3 minus lambda, minus 0. Then minus negative 4, so plus 4, times the determinant of this two elements with this two, negative 2 times 3 minus lambda, remember we're subtracting lambda off the diagonal, minus 0 times 4, plus 3 times this 2 by 2 determinant, negative 2 times negative 4, minus 1 minus lambda times minus 4. So we need to set all of this equal to 0. So expand all of that out. You end up with negative lambda cubed plus lambda squared plus 5 lambda plus 3 is equal to 0. This factors as negative lambda minus 3 lambda plus 1 squared. Okay, so there is the totally factored characteristic polynomial. So there are two eigenvalues, 3, which has algebraic multiplicity 1, and negative 1, which has algebraic multiplicity 2. Well, the eigenvalue of 3 had algebraic multiplicity 1, so we're only looking for a single eigenvector, so we just go ahead and set up that the matrix times a column of unknowns is 3 times that column. After a little bit of work, which is kind of old hat by now, one possible solution is 3 minus 3, 2. The eigenvalue -1, however, has algebraic multiplicity 2. So we're hoping for two linearly independent eigenvectors, but we're probably not going to find them just because of what section this problem is appearing in. So we go ahead and set up that A times the column equals -1 times the column. First row gives us this equation. Second gives us this. Third gives us this. I've preemptively added an A and a B and a C to every side over here. Okay, so you would end up with -3A, but then in the top row, you'd add an A to that. Here, you would end up with a single B, and then you would add a B to that, giving us 2B. So in other words, instead of setting up A times the vector equals lambda times the vector, I'm doing A minus lambda of the vector equals 0. Okay, so that's what we have here. So we have three equations. The middle equation, with no C in it, directly tells us that A equals B. Once we know that A equals B, the third equation gives us that C is equal to 2A, as does the first. The first and the third are now redundant with one another. So for the eigenvalue of -1, for an eigenvector of the form ABC, we found that we must have A equals B and C is equal to 2A. We see now that if any of these numbers is 0, then all of them are. But remember, an eigenvector is not allowed to be all 0. So we conclude that in this eigenvector, none of the entries are 0. However, if any of A, B, and C are assigned a value, the others are automatically determined by the equations A equals B and C equals 2A. So once a single entry has a value, all three are determined. In other words, I can only find one linearly independent eigenvector for this eigenvalue. Let's go ahead and set A equals 1, which gives us the base eigenvector of 1, 1, 2. So since we only have a one-dimensional eigenspace, we need to start making generalized eigenvectors. But we only need one more. Okay, the algebraic multiplicity of this eigenvalue is 2, and we already have one genuine eigenvector v1, so we only need to find a single generalized eigenvector in order to be done with this eigenvalue. So we go ahead and solve A minus lambda I v2 equals v1, where lambda is this eigenvalue of -1. So if I am subtracting -1i, I am adding 1 along the diagonal. So we end up with -2, 2, 4 on the diagonal, times a column of unknowns is the eigenvector we already found of 1, 1, 2. So here's what we need to solve. We have a matrix times a column of unknowns equals the eigenvector we found of 1, 1, 2. We can write it out in terms of these three equations, but for a change of pace, let's just go ahead and set up the augmented matrix. Okay, 2, -4, 3, 1, 2, 2, 0, 1, -4, -4, 4, 2. So we've got this augmented matrix here. We work to get it into reduced row echelon form, and here's what you'll end up with. Here is reduced row echelon form of the matrix above. The third row tells us C has to be 0. Once we know that C is 0, the second row tells us B must also be 0. And once we know that B and C are 0, the first row tells us that A must be -1/2. So we can find a generalized eigenvector of -1/2, 0, 0. So we found both an eigenvector and then a generalized eigenvector for the eigenvalue of -1. Then we can write our general solution as C1y1 plus C2y2 plus C3y3, where y1 is the eigenvector corresponding to the eigenvalue of 3, which had multiplicity 1, therefore geometric multiplicity 1 fills our needs. However, for the eigenvalue of -1 that had algebraic multiplicity 2, we only have geometric multiplicity 1. We found one linearly independent eigenvector, 1, 1, 2. Then we found a generalized eigenvector, so our second solution here is -1/2, 0, 0, the generalized eigenvector, plus t times the original eigenvector of 1, 1, 2, times that exponential e to the minus t. Third example, find a general solution, y prime equals matrix times y, and it's another 3x3 example. Well, with the aid of a computer algebra system, okay, there's only one eigenvalue. The characteristic polynomial has a single root of algebraic multiplicity 3, 27. Furthermore, the eigenspace, again with some work, is only one-dimensional, spanned by, for example, 1, 2, 2. So once you go through the work of finding the single eigenvalue, and then you go through the work of justifying that, in fact, there is at most one linearly independent eigenvector, and we can choose 1, 2, 2. What we have to do is begin constructing a backwards generated maximal Jordan chain from this eigenvector with this eigenvalue. We actually already know that we have to find a chain of length 3. If we were only able to find a chain of length 2, our procedure would say start over with another linearly independent eigenvector, but there aren't any. Therefore, the procedure can't terminate at a length of 2, so we must be able to find a chain of length 3. So in order to find a generalized eigenvector, we start off by saying, I want A minus lambda I v2 to equal v1. Lambda was 27, so we subtract 27 off the diagonal, and here is A minus lambda I. Here is my unknown vector v2, but here was the eigenvector 1, 2, 2. So we get two useful equations. Notice, by the way, that the second and third rows will give us exactly the same information. But the first and second row give us these two equations. So negative 12a minus 18b plus 24c must equal 1, and negative 24a plus 12c must equal 2. So we've got these two equations, and we're just looking for any solution to them. If we cancel the a's from the two equations, for example by subtracting 2 of the top equation from the bottom, you'll derive that 36b minus 36c is equal to 0, which means b must equal c. So as long as b is equal to c, we've got a solution. So we can let v2 be any vector for which b is equal to c. And the simplest one I can come up with is 0, 1, 1. So 0, 1, 1 is a generalized eigenvector associated to the eigenvector we started with. Then we have to find the next element in the Jordan chain by solving a minus lambda I v3 is equal to v2. Now a minus lambda I is the same matrix it was before. v3 is now a column of unknowns, but v2 is the generalized eigenvector we just found, 0, 1, 1. Note again, the bottom two equations are identical to one another. So we really only get two equations out of the top two. So with these two equations, we just need to find some solution. If we cancel the a's just like we did before, we'll end up with 36b minus 36c equals 1. And we only need to find a possible solution. So we let b equal 1 over 36 and c equals 0. And we might as well let a equal 0. It genuinely doesn't matter. So here is a choice for our next generalized eigenvector in the Jordan chain. So even though there was only a single eigenvalue, and even though that eigenvalue only had a one-dimensional eigenspace, we have found a three-dimensional basis for the generalized eigenspace. The order in which we found them was, we started with the eigenvector 1, 2, 2. By solving a minus lambda I times an unknown equals this vector, we were able to deduce that v2 could be 0, 1, 1. Then, by setting up a minus lambda I times an unknown equals this vector here, we were able to deduce that one possible choice is 0, 136, 0. So the general solution is going to be c1, y1, c2, y2, c3, y3. y1 is a solution that first incorporates this eigenvector. y2 is the solution that first incorporates this generalized eigenvector, and y3 is the solution that first incorporates this generalized eigenvector. Specifically, y1 is the eigenvector times e to the eigenvalue t. y2 is the generalized eigenvector plus the original eigenvector times t, e to the 27t. y3 is the next generalized eigenvector plus the one before it times t plus 1/2 times the original eigenvector t squared, e to the eigenvalue t. And here we have three linearly independent solutions to the original differential equation. All right, what have we done? When an eigenvalue is deficient, in other words, the geometric multiplicity is smaller than the algebraic multiplicity, we can still find linearly independent solutions to the differential equation in sufficient quantity by finding generalized eigenvectors rather than just standard eigenvectors. Mechanically, the way we find the necessary solutions is by backwards constructing maximal Jordan chains, beginning with eigenvectors for each eigenvalue. The theory of the process is really much more intimidating than it is in practice. In practice, it's just a whole lot of linear algebra and following a fairly straightforward algorithm. Also, if this is a problem that you are doing in an undergraduate class, it's probably no larger than 3 by 3, which means a Jordan chain is going to have at most 3 elements in it. So it's generally not that much work when you actually have to do it by hand. And if you aren't doing it by hand, this is pretty easy to code for a computer to do for you. However, what about characteristic polynomials that have irreducible quadratic factors? We have not yet accounted for a characteristic polynomial with a complex root. In other words, a complex valued eigenvalue for a matrix.